सदा नमस्कार, सुस्वागतम, अभिनंदन, केम छो, वणकम, आदाबा, सत श्री अकाल, राम राम, राधे राधे, जय श्री कृष्णा, ए वेरी गुड आफ्टरनून। मैं अनिल भारद्वाज आप सभी का पीआरएल के 111वें अध्याय में स्वागत करता हूं, अभिनंदन करता हूं। I, Anil Bharadwaj, very warmly welcome you all to 111th PRL का अमृत व्याख्यान। We started the PRL का अमृत व्याख्यान with the sankalp that every Wednesday at 4 p.m. we will have the Amrit Vyakhyaan, and it was a part of the celebration of PRL's 75 years of completion. As we all know, PRL is established by Dr. Vikram Sarabhai in the year 1947, and this PRL ka Amrit Vyakhyaan also coincided with the Azadi ka Amrit Mahotsav, which is to celebrate the India's 75 years of independence. The PRL ka Amrit Vyakhyaan is delivered by distinguished personalities, renowned personalities from different disciplines of science and technology, engineering, business, law, management, culture, sports, music, medical, commerce, and whatnot. Today, we have yet another very distinguished Vyakhyaan with us, Professor Minna Palmroth, who is a professor at University of Helsinki in Finland. And she is going to give the Vyakhyaan on Space is the New Black. It's a very exciting title, and I hope that we will have a very exciting Vyakhyaan also today. I thank Professor Palmroth for accepting our invitation and to be with us today at the 111th PRL Kamrit Vyakhyaan. I would now request my colleague, Professor Nanjita Shrivastava, to kindly introduce today's Vyakhyaan to the audience at that WebEx panel, as well as those who have joined us live at PRL's YouTube channel. Over to you, Professor Nanjita.
Thank you, Professor Bharadwaj. It is indeed my pleasure and honor to introduce today's speaker, Professor Minna Palmroth, who is a professor in computational space physics at the University of Helsinki. Presently, she is holding the position of director of two Finnish centers of excellence in research of sustainable space and in space resilience. Professor Palmroth became the head of the department at the Finnish Meteorological Institute in 2011, where she led research in fields ranging from radar and space technology to Earth observation and space weather. She also held several significant positions of trust, including that of Finnish delegate in the Science and Technical Group of European Weather Spacecraft Organization, or EUMETSAT. Her research interests have a wide range from fundamental plasma physics and space weather to high-performance computing and supercomputer technologies. Her research also includes the physics of near-Earth space, its implications to the societal infrastructure, and the sustainable space economy. Her key areas of expertise include the global energy circulation within the magnetosphere-ionosphere system and modeling in both the MHD and ion kinetic regimes. Professor Palmroth is leading the modeling of near-Earth plasma environment using the world's first global hybrid Vlasov simulation code called Vyakhyaan, and these efforts by her as the PI of two prestigious European Research Council grants that she has won. Vyakhyaan has brought about a paradigm shift in modeling the space environment, and it has enabled the discovery of new phenomena that were not imaginable previously. Professor Palmroth has been recognized for her efforts and has been selected as an Academy Professor for 2026 to 2031, and also director of her second Center of Excellence concerning the resilient use of space. Professor Palmroth is a member of the Finnish Society of Science and Letters, the Finnish Academy of Science and Letters, and the Finnish Academy of Technological Sciences. She is also known internationally for her and held important positions of trust, like a member of INFRAG committee, which advises on Euro HPC supercomputer infrastructure. She was the chair of the Space Advisory Group for the European Commission. She is highly active both in outreach and societal impact, and is personally very much interested in coupling science and research with the public and private sectors. Due to this, in 2022, in recognition of her actively uh, and highly active outreach efforts, societal impact work, and policy advising, she received the JV Snellman Prize. And in 2023, she was awarded the prestigious Copernicus Medal for her scientific achievements. So, with this brief introduction, I would like to invite Professor Palmroth for delivering today's distinguished lecture, which we call as VRL Ka Amrit Vyakhyaan. Professor Palmroth, the floor is yours and you can share your screen.
Thank you so much, Professor Anandita. This was very kind, indeed, very kind introduction, and also very kind of you, all of you, to invite me to your prestigious lecture series. I'm very honored to give this talk today. So I shall try to now share the screen and let's see how it goes. Let's see. I have to do it again. Sorry, this takes a little bit more time than we were practicing this, but window, here it is. Share this window. Now, I think you see, and I will put it into the
presentation.
Right.
Perfect.
Wonderful. So thank you so much again for inviting me to your lecture series. I'm very honored. And this is the title of my talk. And I am thinking about the contents of the talk by 3 spheres. Very often when people are talking about sustainability in general, sustainability of the earth, the way to framework or frame this sustainability is to talk about something that has to do with the environment, something that has to do with the economy, and then the society itself. And the idea is that sustainability is found in the middle or the intersection of these 3 spheres. So this will now be my framing for this lecture. So I will talk about space as an environment, then space economy, and then also people that are using the space services, and also the critical dependencies that the society has on space. And this is then framing the field of sustainable use of space. But let's talk about the economy first. So space is a mega trend. Here you can see all of the satellites that were launched to space since 1957, the first satellite that was launched to space. And you can see that the during the Cold War era, there was about 150 new satellite launches to the space. But if you look at the latest numbers of launched satellites, you can see that this launching of satellites has increased exponentially. And we are now launching more satellites to space than ever before. And if you are looking at the colors of these bars, you can see that the motivation to launch these satellites to space is economical. So it is the companies who are launching satellites to space in exponential speed in hopes of getting revenue, getting economical benefit from utilizing the space. There are all kinds of different estimates about the space economy and how much is it growing. This is one estimation. For example, in 2023, the entire space economy was around $630 billion, but it's estimated to grow to around 1.8 trillion or more dollars in the next 15 years. And here are also the projected new satellites and constellations that are being planned to being. So this shows that the plans to use the space is not decreasing, it is increasing. Finland is here not at all kind of something which lags behind, but we are actually the second most important new space economy country in Europe. So in Europe, UK is leading the private investments into space technology, but Finland is second in European countries, leading countries like Germany, France, and Italy, which are the kind of traditional space countries in Europe. Here you can see the situation in the world. You can see that India here is 6th in the world in terms of getting private investments to space, but Finland is not very far behind, so 7th in the world and again 2nd in Europe. So United Kingdom is leading in Europe and worldwide United States is leading. Now if we go to the society, then talk about what are the users of space infrastructure and also the critical dependencies that we have on space. Space is actually nowadays so mundane. It is so part of our modern way of life that it's almost boring already. There are many applications that are depending on space usage. For example, positioning and navigation satellite signals, which give you, for example, your map navigation routes on your mobile phones. Time synchronization is extremely important. So many systems, for example, in banking and mobile networks, they utilize a synchronization signal that's coming from GNSS satellite. And this is then used to put the mobile phones, for example, in time with the masts from where the signals come. Earth observation is also critical. We have nowadays agricultural products that are entirely driven by space and Earth observation services, forestry, whether there are flooding or droughts, that's also very often determined by Earth observation services. We also have verification of insurance claims by satellite, which is actually a business case for one of the Finnish new space economy companies. Weather forecasts, of course, could not be done without space. Climate change and monitoring of the planet in general is based on space, and then satellite TV defense. And I don't think we have seen all of the services that are based on space yet, but these are growing and expanding as we go into the future. Now, if we go to the orbital space and look at the space as an environment, there are two things to consider in orbital space. One is the debris component, so space debris, those chunks that have been left to space, and then the other one is called space weather. So similarly as we have a weather here on Earth, we also have a weather in space. Let's talk about the debris first. So at the same time as we have been launching satellites into space, of course, by Newton's laws, those objects will stay in space if there is no force which is going to take them out of space. And the force which is, there are two forces that could take satellites and orbital debris particles away from space, and these are atmospheric friction and also then propulsion mechanisms. Here you can see all of the total objects. This is not all of them. only those which can be monitored from ground. So there are radars and other technologies that can monitor those debris particles and in space, but only those which are larger than 10 centimeters can be tracked. And in fact, there are millions and millions of smaller particles also in space, but these are only the ones which can be monitored. Anyway, you can see a very large increase of total objects. Here are the satellites on blue, but then fragmentation debris, mission-related debris, and all of the other types of debris is also there. You can see also a couple of jumps or sudden increases. These are collisions of satellites or so-called anti-satellite tests. So a country has decided to show to the other countries that they can launch a missile to space and hit their own satellite. So no country has yet sent an anti-satellite test or a missile to somebody else's satellite. They have only shot their own satellites, but anyway, this capability is there and already started in the 80s. Here are objects on polar orbit. So polar orbit is an orbit which is circulating the Earth through the poles, the northern and southern poles. And here again on red, you can see those debris particles which can be tracked with the technologies that are in place right now. And on orange, you can see those objects which will be monitored with the future technologies. But in blue, you can see those objects that are really there. And this is, of course, those much of these debris particles which are on the 750 and 1,000 kilometer altitudes are actually coming from these two collisions, China's anti-satellite test and then this Iridium and Cosmos satellite collisions. So actually there is already in space a layer of debris where people don't want to put their satellites, because now here on green you can see those satellite missions which are planned, and you can see that those missions are not planned to this debris cloud, but either below it or above it. And of course it means money to the companies, because either they have to utilize more sophisticated technologies to see from above the debris cloud, or then more propellant, so that they can keep the station and the orbit as they want for the satellite. This is a zombie satellite. This is one of the largest debris particles. This is a bus-sized Envisat vehicle, which is a zombie. So, and actually it is exactly on this orbit here on 750 kilometer polar orbit. And why is it zombie? Is because the ground control has lost the controlling capability for Envisat. And actually, if Envisat collides with any satellite, that orbit will be closed basically forever, because there is currently no way of cleaning these little pieces of junk away from the space, but they are just orbiting there and causing problems for the satellites. Also, small chunk particles are also a problem. This is not a bullseye in a car's windshield. This is a bullseye on International Space Station window, and it has been hit by a very small debris particle, a paint flake, perhaps milligram weight paint flake, which has hit the window of the International Space Station. If you calculate the momentum of 1 milligram weight paint flake in space, it actually is the same as a fist-sized rock which hits your car windshield on a motorway. This is because all of the space particles which are orbiting in space, they are orbiting with 7.5 kilometers per second velocity. Here are some debris scenarios. This is a journal game theoretical analysis in a journal called Games. And if we don't do anything, the threat is a so-called Kessler syndrome. So those particles will start to collide with other particles, and eventually, even though you would not put any other satellites or space objects into space, this Kessler syndrome would make space unusable in the long term. But then if you take satellites away from space and do it very cleverly, you can actually preserve the space as an environment also for the future generations. There are no binding international agreements in using the space. There are only non-binding international agreements. For example, the Outer Space Treaty, which is a treaty by the United Nations in 1967. However, there are national legislations which is binding. So, for example, the Finnish companies which launched to space, Finnish legislation is binding them. So, how to control those launches actually is quite a difficult task also for legislators, because there's no international agreement, only non-binding agreements. But then what you can do is to bind those users of space by national legislations. Right, and this is our first Center of Excellence. It's called Research of Sustainable Space, and what our Center of Excellence wanted to do, it is now ending this year, and we are then moving to our next Center of Excellence called Resilient Space. But then anyway, in this Center of Excellence, we wanted to investigate the conditions in space and develop radiation-tolerant satellites and also cost-efficient deorbiting technologies, so that the satellites which are launched into space are not contributing to the existing debris after the mission. And the objective was a significant improvement in orbit safety. And now let's go to the other environmental issue in space, and this is called the weather in space. Some people in the audience perhaps already knows this, but similarly as we have a terrestrial weather, we also have a space weather. Here's the definition. So those physical conditions in the near Earth space that affect technological reliability or human health. Human health very often is concerning those International Space Station people and also polar orbiting aircraft crew, but not people on ground here, which are shielded by our atmosphere. There are two causes for space weather: solar eruptions, of which you can see an example here, and also the dynamics of the Earth's own magnetic field, which I'm talking about in a few slides. Strength varies. There are several small storms per year, then perhaps medium-sized storms once per 10 years, and then megastorms once per 100 years, or even larger storms once per 1,000 years. And the impacts, the most important for society: power grids, satellites, and all kinds of signals which use the electromagnetic spectrum. So satellite signals, radar and radio signals, etc. So as many of you already know, we have a big bar magnet inside our planet, and this spreads into space and forms this dipole geometry, and that interacts with the solar magnetic field, which is spreading from the sun to the interplanetary space. These dipole fields, they converge towards the polar areas. I am here right now in Helsinki, which is in southern Finland, and this because these magnetic fields converge towards the pole, this is the magnetic pole here in the center, they act like railways to the particles in space. So those particles are coming where those magnetic field lines are guiding and leading them, and therefore they create this large auroral zone where you can see aurora. And this auroral zone typically in nominal position is in Finnish Lapland. So if you want to see the aurora, the best chance to see them is go to Finnish Lapland, where you can statistically see them once per every second night. Here in Helsinki, statistical observation frequency of the aurora is once per month. Here is a three-dimensional picture of the situation. So actually these auroral zones are not only just kind of nice things to do and nice things to see, they are delineating those space weather which I was talking about. They happen in this kind of cone of influence. So the Earth's magnetic field guides impact to cones delineated by the auroral zone. There are also different types of space weather phenomena which are more in low and mid latitude, and I bet you guys know more about that than I do, but what I'm normally doing is this polar space weather phenomena. What is interesting in about the magnetic latitude and the intensity of the space weather impacts? So the northern lights, those once per month, they basically can be seen on latitudes, which I'm showing here on red. A few times per 10 years, there's a storm which takes the auroral zones to a little bit more southern latitudes, and during those megastorms, once per 100 years, auroral zones will spread to very much lower latitudes. And here you can see a cartoon. If you see aurora here, it's normal, and the lower they are in latitude, the more there are open questions which the solar terrestrial physicists want to answer. So basically the vicinity of the auroral zone is where the strongest space weather impacts occur. Here's one example of the space weather impact. So this is controlled by Earth's own dynamics. So here you can see NASA's SAMPEX satellite measurements of so-called killer electrons. So electrons which are going at the speed of light or almost at the speed of light. And those are trapped by our Earth's magnetic field, which acts as kind of puts those particles to bounce back and forth between the two poles, the northern and southern poles, and makes the kind of the space very much a radiative place. So there's a lot of radiation. These belts are called the radiation belts or Van Allen belts. And why is important to satellites is because there are even single particles which can affect the satellite health. There's aging due to continuous radiation dose within these radiation belts, and also spacecraft charging occurs in these radiation belts. And why is this a problem for the society? Is because the critical infrastructure, the navigation satellites and also the weather satellites, they are embedded in the radiation belt. So we really need to know about space radiation and what causes it, so that we can protect those very expensive satellite infrastructures that we have in space. The same particles which precipitate from the outer space to the auroral zone and cause the aurora, they change the conditions in the upper atmosphere. And when there is a signal that is going through those changed conditions, these signals can deteriorate. They can absorb, refract, and scintillate, and this can change the signal amplitude, frequency, and phase. So these signals can even altogether be lost. And this is, of course, a problem for navigation devices. It's also a problem for satellite-based timestamps. They can close the polar cap for aviation routes, and which has happened actually quite often, and also cause radar signal degradation and loss. The same particles which precipitate from outer space and cause the nice aurora, they also carry electricity, and in the end they will make these mega-ampere current systems in the top side of the ionosphere, and these current systems induce a ground electric field on ground, and this ground electric field drives DC currents in all long conductors, such as the power networks, gas pipelines, railways, any thing which is conducting and long. You can have extra DC currents because of these mega-ampere currents in the top side of the atmosphere called the ionosphere. The space weather impacts, these power grids actually can even be tripped during these large storms. For example, in Malmö, Sweden, they had a power network tripping in 2003, and then also in Canada in 1989 the power network was tripped and these effects can last from hours to days. So that was the normal bit, but let's now then go to the extreme storms. This is a story from September 1859. So in September 1859, Rocky Mountain gold diggers woke up in the middle of the night because it was said that the aurora was brighter than the full moon, and you could read in their light. And anyone who has seen aurora understands that this is extremely unusual, because normally aurora is very faint and you can barely see it on your plain eyes, but if the people were able to read in their light by historical records, it means that something very unusual has happened. And here you can see the auroral sightings during this September 1859 event. And here the background is the magnetic latitude. So the bar magnet inside the planet is not straight, but it makes a little bit of a twist. So therefore this magnetic latitude is not a straight line, but has this curved nature. This is the magnetic equator, so zero contour here, and you can see that normally when these aurora typically are here in the Finnish Lapland, but then during this 1859 people were seeing aurora as far south as Caribbean. Now this means that the cones of influence, which I was talking about in the beginning, so the area where space weather effects occur, actually was spreading almost to the entire globe. And now I'm kind of drawing the city of Mumbai here in India. Here is a Mumbai magnetometer recording from 1859. So already at that time in 1800s, we already had magnetometers recording disturbances, and this disturbance, which was recorded in Mumbai, is of the same magnitude as the storm which tripped the Swedish power network in Malmö in 2003. So also people in lower latitudes will be affected if the space weather event is strong enough. One way of measuring solar activity is by number of sunspots, and this was already started by Galileo Galilei in 1600. So he calculated the black spots on the solar surface, and it has been then followed up centuries after that. And what people have seen is that there is this 11-year variation in the number of sunspots. So sometimes the sunspots there are many sunspots, and sometimes there are a low number of sunspots, and this is an 11-year cycle. Now I'm drawing here those great storms. And how do we know that they are great? Because low latitude people saw aurora and were so stunned by the show that they wrote to a historical record that now there's some lights on the sky and we don't know what is going on. And then there have been people who have been digging out these historical records and by that deducing that there has been a great storm. There are also other ways of reconstructing the space weather than just the historical records, but this is one way of doing it. Here's the Carrington in 1859 with I was talking about. There was almost as large event in 1921, but not as large. And then, of course, we had a near miss in 2012. This was launched by the sun, but it missed the Earth by a couple of days, measured by NASA stereo satellite, which saw that the driver of the was Carrington scale, but this cloud did not hit Earth. And then, of course, we don't know when the next one happens, but since we know from historical records that these are basically happening once per 100 or 150 years, we know that there will be as large event in the future as well. This is a statistical recurrence likelihood. So sun doesn't have any reason to launch them once per 100 or 150 years. Sun could launch them twice in a year and then wait for 300 years and still the statistical recurrence likelihood would be once per 100 and 150 years. Here are also some different ways of estimating. This is one of them. Chapman et al. Said 0.7 annual recurrence risk. This is a figure of the sun from 2014, and the spot in the middle is as large as the Carrington event spot in 1859. I led a Research Council of Finland project called Carrington a couple of years ago, which was a 3-year research project which was assessing the impacts and developing risk mitigation for these extreme scale storms. And we had a consortium between the University of Helsinki, Finnish Meteorological Institute, and then we had a small company also within the consortium. And now I'm talking about the results per technology, what we found in this project that we wanted to see whether the Finnish critical infrastructure is space weather proof. Here are the research questions of the projects. We wanted to see the strength and geographic extent of geomagnetically induced currents, so these power grid risks. We wanted to see the flux and energy of particles on satellite orbits to see what the satellite risks are and also the impact on navigation. And of course, the methods has to be modeling, because if we had observations of events of this scale, we would not have to speculate what happens because we would already know. So the only way to prepare the future is by modeling. And here are now the geomagnetically induced currents. So we think that in this red area, there will be very powerful GICs, so powerful that the power networks are in danger. And on the yellow region, there are also some GICs and some power networks can be vulnerable. So what we used as a threshold value is 10 millivolts per meter. So if the device can endure 10 millivolts per meter, it is safe, but then even a geoelectric field of this size can drive very large DC currents in long conductors. Finnish power grids will most likely endure because we have a good power network and good transformers. But one of the greatest risks is actually in the US, because their power network is quite old and they don't have very good transformers. So they are actually quite alarmed to these very powerful space weather and events, and they are also the only country in the world which has legislation against space weather. I don't talk about these internet name servers. Here I go to the satellite health. So what we calculated here is that the expected total dose due to relativistic electrons is equivalent to the dose that would be accumulated under normal conditions in 100 years in the LEO orbit. So LEO orbit are these satellites which are around 500 and above that altitude, 500 kilometer altitudes or above. And then 5 to 20 years on medium Earth orbit where the navigation satellites are, and then on geostationary orbit also the same. So there will be aging, for example, by the solar panels on those orbits. And then also there is a threat to have solar energetic protons, which can corrupt the satellite in satellite memory. So we calculated that there might be about 1 bit flip per gigabyte per second that would occur on those satellite memory systems. And this means that the so-called old space satellites, so satellites which are built, for example, by European Space Agency or NASA or big organizations which use good components and good testing measures, they could go to a safe mode if they saw this kind of a flux of solar energetic particles. But then there's these satellites which are launched by the companies, those new space economy companies, which I was talking about in the beginning. Those satellites will likely start rebooting if they see a flux of solar energetic particle like this size because of the memory corruption, and the ability to continue after the storm of those is under a major threat. So we estimate that the privately owned satellites actually can be in very grave danger during these extreme storms. What does it mean if a satellite goes to a safe mode? It means that they will not provide timestamps, navigation or positioning signals or any other data. So the satellite will go to, if it goes to a safe mode, it just receives commands from Earth but doesn't give anything back. And this means that if those satellites go to safe mode, it also means that these timestamps and navigation and positioning signals and other data can be lost at least to the duration of the storm. And then whether you can get those data back after the storm is of course a function whether the satellite endured in space or not. If it was broken, then it has to be replaced to get those signals back. Here is again the magnetic equator, and here on background you can see the flight routes on Earth, and we estimate that the polar caps could go such that the signals could be deteriorated in this area, and also of course here on the southern area. So this means that this is a problem for flight routes, because now if the satellites, the aircraft cannot fly because they don't have signals from ground, if the radio signals are cut from ground, then those aviation needs to be at least temporarily stopped in these areas. It's not only about the signals in the polar caps, but it's also the radiation dose. This is a paper by Xu et al. 2023, which was looking at the Halloween storm. This is the 2003 storm. That was a much smaller storm than the 1859 Carrington storm. And it saw also, this paper was speculating those what those conditions would mean during a Carrington storm. This shows a map of increased radiation dose on flight altitudes And during a Carrington storm, this 1859 scale of event, the estimation is that those aircraft couldn't fly because the crew would get such a large radiation dose already from those particles which are coming from the space and precipitating to the atmosphere, ionosphere and atmosphere. Mobile networks. So this is a slide which I made with a mobile network expert, and we were looking at the 90% of the GNSS receiver shipments go to the telecommunication sector. And one of the things in mobile networks is that they need precise time. So they need they very often take it from the GNSS satellites using these receivers. And since those navigation signals and the time synchronization signals can deteriorate during those very large storms, it might be possible that those signals are not available for the mobile networks during those large storms. You can prepare by having an atomic clock. This is a ground-based clock which gives a clock signal for the network, and at least in Finland, the teleoperators do have atomic clocks, but there might be mobile network operators in the world globally which only have the GNSS receivers to have the mobile networks synchronized. And if this is the case, then these networks can have problems during these very large storms. Then there's also a possibility that the satellites start to re-enter during these very large scale storms. And this has to do with the fact that these mega-ampere currents, which I was talking about, they heat the thermosphere, which lifts upward. And when the thermosphere is lifting upward, it increases the friction on satellites, which are like around 500-kilometer orbit or around there. This is an example of satellite tracking problems from 1989 storm. This is the storm which tripped the Quebec power network. And here's the storm on yellow. And on blue, you can see all of those satellites which were temporarily not where they should be due to this exact increasing of friction on there. So those satellites came downwards a little bit until they were tracked again, and some of them came also down. And if this Carrington scale storm occurs, this re-entering of the satellites might occur. The economic impact of these very large scale storms can be very large. There have been calculations of, and you can get basically into any, I mean, if the power network trips, it's a primary commodity for many things. And for example, this Lloyd's estimated that it could cost like 2.4 trillion, but these are of course all estimations and speculation. Principle for nominal space weather prediction is here. So first we have the sun, which gives the solar wind. Solar wind is observed in Lagrange 1 point by satellites, or then you can model the solar wind propagation from the sun, which is here, the black, and then you can model this, how these clouds eject and how they propagate in the interplanetary space by models such as Euphoria. And then you get the physical description of the solar wind and put it into a real-time model. And then in the future, not yet, but in the future, that might give you a forecast, for example, for the power networks, how large GICs or geomagnetically induced currents would be seen. The problem is here that if you use the Lagrange 1 point measured properties by the satellite, the lead time is only about 1 hour or less, and the accuracy is very poor. So these models are not very good in predicting the space weather. If you use the model or the solar wind conditions based on a model, this is very poor prediction. So these space weather models are not good enough yet so that we could have a good lead time, but the models do not predict the right solar wind conditions. The scenario how this would go would be that if the sunspot appears in this area and is erupted in this area, then there would be a 24/7 space weather center, for example, at the Finnish Meteorological Institute, which would see this eruption of a sunspot, and then it would give a warning for the authorities that now there's a big sunspot that has been erupted in the dangerous zone. However, the physical impacts cannot be determined before those are measured by the satellites, and those satellites are so close to the Earth that the lead time is very small, as I said. How to monitor the current situation? Here's the situation right now. This is a so-called storm index, so DST index, which is measured in nanoteslas. Right now we don't have so much interesting things happening in space, so the space weather is nominal today. This is the last large storm which was observed in May 24, so-called Mother's Day storm. However, even this storm was around 4 or 5 times smaller than the Carrington scale storm. So it has been estimated that the Carrington storm DST index would have been around minus 1500 nanoteslas, and you can see here that the May 24 event was only 400 DST. So in summary, I was talking about the debris. Worst case scenario is the Kessler syndrome. And then I was also talking about the Carrington level extreme space weather, which could cause wide and simultaneous impact from power grid to communication and logistics. And the likelihood is that the Carrington event was 166 years ago, and we haven't seen any such events during the industrialization era. Thank you very much. I hope I was in time for you, and if you have any questions, I'm more than happy to answer.
Thank you, Professor Palmroth. It was very interesting and very insightful lecture, and I'm sure this has generated several questions and queries in the audience. So I would invite my colleague, Dr. Manas Samal, to conduct the question and answer session. Manas?
Yeah, thank you, Professor Nandita. And Professor Palmroth is really indeed very good comprehensive talk covering a very wide area, starting from space environment to space weather and dynamic phenomenon and its implication on our economy. So I'm sure we may have some questions. So I would invite my colleagues to raise your hands if you have questions. Then then you can communicate with the speaker. Similarly, if there are questions in the YouTube, I can also read those questions, and that can be discussed. So please raise your hands to communicate with the speaker, Professor. So I have one question. So you talked about that the 10 millivolt kind of threshold.
Yes.
That's typical for the geomagnetic storms, or it is kind of in a high value state?
This is a very high value, and we were utilizing it like as a rule of thumb that these very extreme storms could cause 10 millivolts per meter or larger, and this is a threshold value which is utilized, for example, by the Finnish power grid companies to estimate the power network failures. So this is a kind of a good estimation of the overall magnitude, how large the geoelectric field could be.
I see. And when there are kind of extreme sun where we have a kind of highly extreme coronal mass ejection, so in that case, this threshold could go very high. Is it so?
Yeah, so the larger the storm, the larger the geoelectric field. So, and of course, I mean, the larger it is, then the more the societal kind of the critical infrastructure owners need to be concerned about what happens.
Okay. So these these predictions, what you talked, that you kind of now setting institutes where you will be modeling and predicting those behaviors, so that we can save at least some of our power grids. Okay.
Yeah, indeed. So, so what we do here in Finland is that we work together with the power grid companies and such that we give them the kind of our estimation of how large the geoelectric field would be, and then the power companies will estimate whether their power network will stay operating in these conditions. And then, I mean, if they would observe that the power networks would trip or would be in danger, then there is a possibility for them in advance, since we have already worked together, to mitigate those by, for example, identifying those critical transformer positions, or having some other equipment installed which can then improve their chances of enduring those very large storms.
Okay. Yeah. Thank you. So yeah. So I again ask my colleagues, please.
I have questions. That raise hand option is not working. So this is Vijay Shah. Yeah, thank you, Prof. Minna, for this wonderful talk. So I have a few questions related to your computational approach. So for all this like modeling and simulations, so do you use classical electrodynamic equations, or there are some quantum mechanical effects also you take into account for precise estimations of all the things like for accuracy?
This is an excellent question. Thanks very much. So the space weather modeling predictions right now, as I was talking, are actually not extremely good right now. And the problem for that is that those, for example, the solar wind propagation models, they are all based on MHD, so magnetohydrodynamics, and also those global space weather simulations which predict or look at the forecast situation in the near Earth orbit, they are also based on magnetohydrodynamics. And magnetohydrodynamics is an approximative method. However, it's the only method which can be ran real time. So all of those methods which are more accurate, for example, the ion kinetic methods or fully kinetic methods, they are so computationally heavy that their execution is so slow that we cannot get those forecasts in time. So therefore, and this is a problem because now if we really want to know what happens to the critical infrastructure, we would of course want to have some accuracy, but then we have to use supercomputers and other very difficult technologies to really predict what's happening, and this is currently not possible to do real time, and that's why we need to utilize those approximative methods.
You need supercomputers for only studying dynamics, or for doing numerical calculations?
I mean, all kinds of models are used in different scenarios, but I mean, if I'm talking about, for example, the global magnetospheric behavior, then we of course need to understand the dynamic situation using those models. But I mean, different people in the world are utilizing different methods of estimating the system.
Yeah, just last question. So for this all these simulations, you must be also needing some kind of input, some atomic or some scattering cross sections or like that. So may I know what kind of for like some boundary conditions?
Yes, excellent question. Yeah, so typically a near Earth space simulation works such that it takes as an input the solar wind conditions, and then it propagates the kind of the plasma conditions using some equation set, for example, magnetohydrodynamics or some other approximations. But solar wind input is the most important boundary condition, and also the Earth's dipole field is another boundary condition.
Okay,
Thank you very
so
much.
yeah. So if there are issue with raising hands, please you can you can talk directly to the Professor Minna. So please, we can take a couple of questions.
Hello.
Yes, I see Satendra. Please go ahead.
Yeah. Hello, am I audible?
Yes, yes, you are audible.
Good afternoon, myself Satyendra, and working on the space weather effects on the Venusian ionosphere. So my question is regarding the glaciator. So if we want to use this model for the case of Venus, what type of the initial conditions and boundary condition we would like to include in the model because there is the limited observation around the Venus.
Yeah, indeed. So Glaciator is an open source model. It's under GPL2 license, so it means that it can be freely utilized by anyone. And indeed, lately we know of people who have, for example, utilized it for Mars, and there's also a version for Mercury. So it means that if you guys want to utilize it for Venus, that's totally possible. And so basically how it happens is such that you go to Git repo of Glaciator and then download the code and then make a configuration file that has to do with your system. So in this sense, the Venus environment, then you run it. You have to secure some supercomputing resources to do it. However, Venus is probably similar as Mars because it doesn't have a very large magnetic field, so it doesn't have to have an extremely large computational resource to be ran. So our colleague in Boulder was running those Mars simulations with Glaciator in their university clusters. So if you have university clusters, I'm pretty sure that the Venus can also be done with those resources. And if you, I mean, also we are happy to help to give you some insight on how to make those configuration files such that you can run your own simulation runs. So we are happy to help with those also.
Sure, man. We will connect.
Yeah.
I would like to connect through some connections.
Satendra, please please elaborate what you want to ask again. One question or?
No, I am just thanking the speaker. Like
Okay.
in future we would like to use this Glaciator for Venus modeling.
Yeah, go ahead and download it from the from our Git repository, and if you have any problems, you can always contact us.
Thank you.
Okay, I see no more hands, so I think we are also on time. So thank you, Professor Minna, for answering all the questions. Now I will invite my colleague, Professor Durga Prasad, to conclude the session. Professor Durga Prasad, please go ahead.
Thank you, Dr. Manas. So we have come to the end of this lecture. So It's my pleasant duty to deliver the vote of thanks. So on behalf of the director PRL Amrut Vyakhyaan Committee and entire PRL family, I thank Professor Minna Palmroth for accepting our invitation and delivering the 111th Vyakhyaan of our popular PRL Amrut Vyakhyaan series. Thank you, Professor Minna Palmroth, for accepting our invitation and providing a very informative Vyakhyaan. Our lecture, aptly titled as Space is the New Black, elaborating on the aspect of vulnerabilities and emerging risks to space infrastructure due to various aspects such as space debris, space weather events, radiation environment, etc. So that may actually affect our ambitious goals and future plans of thriving space economy. Thank you very much. Also, many thanks for patiently answering the questions from our viewers. I thank our director, Professor Anil Bhardwaj, who has been our force through his constant encouragement and support for keeping this lecture series on, which is going on very well in its second innings as well. I thank our Dean, Professor Palmraju, Chair of Amrut Vyakhyaan Committee, Professor Nandita, and Co-Chair Dr. Lokesh, and all the members of PRL Amrut Vyakhyaan Committee and others behind for their constant efforts. Our special thanks goes to Dr. Anshu Kumari of USO for contacting and inviting Dr. Palmroth for this lecture. Most importantly, many thanks to all our participants and viewers who have joined us live through WebEx and YouTube today for this Vyakhyaan. With this, we come to the end of this episode. It's now time to sign off from PRL. Please do join us for our next episode of another interesting and exciting Vyakhyaan. Till then, stay tuned and keep following PRL updates on our website and social media platforms. Thank you. Jai Hind. Namaste.
Thank you very much. Bye-bye.
Thank you. Thank you.
Thank you.
Minna.
Thank you.
Bye.
Thank you.
Bye-bye.
Bye bye. Thank you.